Okay, surprise. We are going to be taking a little bit of a detour. I've got a couple of reasons for doing this. First of all, I'd like you to consider the world outside of things that are strictly clinical or of clinical interest, which is where a lot of people in nursing are. I know this because I went to school at UC Irvine where everybody was a bio major and a pre-med. And I was kind of appalled at my classmates' lack of interest in the things that were really kind of important. And so what I like to think of this lecture as being dedicated toward things I think that you need to know if you're going to be a resident on Earth. Yeah, that's exactly what I said. Things that you need to know to be alive on Earth, basically things about the way that the Earth works in relationship to the sun, in relationship to, and how this actually has some impact on the kind of life that we lead. In particular, specifically in Southern California, right? Another reason is that some of you might very well decide at some point that you don't really like the idea of spending your entire career working with sick people. Yes, sick people are not always the most pleasant of subjects. I think I can personally, I would hate being a nurse. Sick people complain all the time, and for a lot of reasons. I mean, I was never at all interested in pursuing a career in clinical science. Okay, maybe some of you are kind of thinking a lot like me about this, or maybe you will be thinking like me about this later on in your developments. And so it might be worthwhile for you to realize that there's a whole world of biology out there besides what's directly relevant to clinical science. Okay. And so we're going to be starting with, I want you to turn your attention to chapter 34. I'm only going to have you pay attention to section 5, right? So it's just one section of one chapter, 34.5. It does not require a lot of background information, but the title of this is Regional Climate Influences. Regional climate influences the distribution of terrestrial communities, right? And so we're basically answering some really basic questions, right? For example, why is it that it's warmer closer to the equator? Why is it warmer in the tropics than it is in the temperate zone? Why is it warmer in the temperate zone relative to the more polar regions, right? And you know that this is true. I guess the question is, can you identify why that is, right? And the answer is actually pretty easy. Yeah, we know that the sun is coming in. The sun is really a really big star, right? Oh no, I got to change over to my annotate function. Okay. And so the sun is pointing its rays in this direction. It's pretty much perpendicular rays. And I guess the question is, well, how much energy is being received per square foot, per square meter of the Earth's surface? And basically, if you go to the equator, where the let me change, make sure this is right. So if you go to the equator, where the sun is is directly overhead for a greater portion of the year, the sun is incident more or less directly overhead. You actually get a lot of energy. Basically, if the width of this band, from there to there corresponds to a fixed amount of solar energy, it is being spread over a relatively small area if the sun is coming directly overhead, right? But at a higher latitude, closer to the Arctic Circle, at a higher latitude, that same amount of sunlight coming in at this angle, okay, is going to be received over a much larger area, right? Which means that the energy is spread out over a larger space, which basically means that you're going to be having less solar energy incident on the light on the surface of the Earth, which means that you're not going to get nearly as much energy of the sun, right? So yeah, I mean, this means that the equator, tropical regions can support a much higher rate of productivity relative to the polar latitudes, but it also means it's going to be a lot warmer closer to the equator. Okay, and so yeah, I mean, where we are in Southern California is roughly, roughly around 30 degrees north latitude. But the other thing that's incident that you can see here is you've got two lines which correspond to the Tropic of Cancer and the Tropic of Capricorn in the northern and southern hemispheres, respectively. And the idea here is that the Earth is kind of directly pointing at the sun. The equator is directly under the sun at the equinoxes, right? The sun gets higher in the sky and lower in the sky, higher in the sky and lower in the sky. Where we are, the sun never gets directly overhead. Right? It's always a little bit towards the south, at least, or sometimes it's way towards the south. But basically, the sun is always to some degree to the south. We never get overhead. If you were on the Tropic of Cancer, if you were to move further south, so if you were on the Tropic of Cancer, there would be a day, we'd call it the summer solstice, when the sun was directly overhead, right? That would be roughly around June 20th, June 21st, right? June 21st, the sun is directly overhead. If you're higher latitudes of that, then the sun never gets directly overhead. It's always a little bit in a southerly direction, right? Similarly, if you are on the Tropic of Capricorn, which is a little bit less than 30 degrees south latitude, around what is for us the winter solstice, December 21st, is when the sun is directly overhead if you're on the Tropic of Capricorn, right? And like right here in Botswana, right? You're on the Tropic of Capricorn, December 21st, the sun is directly overhead, right? And basically, if you're in the area between, we call these the tropics, between the Tropic of Cancer and the Tropic of Capricorn, that would be the tropics. And that would be the area in which, at least on some day of the year, the sun is going to be directly overhead. Okay? And the reason for that is that the Earth is tilted. And so scroll up a little bit, and it's this degree, this difference between having an axis that points straight up and down, right? If it pointed straight up and down, then we wouldn't have any seasons. It would be pretty much the same kind of, amount of solar radiation all year round, okay? But because we've got a tilt, that means that when the Earth is tilted away from the sun, oops, hang on a second, let me make sure that I'm getting my annotation. In this case, the Earth is tilted away from the sun. At least the northern hemisphere is tilted away from the sun. And that means that the angle of solar radiation where we are in the northern hemisphere is going to be at a lower degree. Whereas if you go to the other direction, and on June 21st, this would be December 21st. Okay. In June 21st, the Earth's tilt is toward the sun, which basically means that the sun is more closely directly overhead. Okay. And this explains the seasons, right? In June 21st, solar radiation is closer to directly overhead, which basically means that we get more energy per square meter compared to what happens during the winter, where up here in the northern hemisphere, we're getting the sun at a more at a weaker angle, right? We're getting less solar energy per square meter during the winter than we are during the summer. That's in the northern hemisphere. Okay? So yeah, the Earth's tilt is basically what causes the seasons. The sun is not hotter during the summer. It's not colder during the winter. The reason why we have summer and winter is because the Earth is tilted, and as the Earth rotates from one side of the sun to the other side of the sun, the side that is facing it is closer to the sun, the side that's tilting toward the sun, alternates between the northern hemisphere during our summer, and the southern hemisphere during what is our winter. Our winter is the summer in the southern hemisphere. I'm hoping you know that, right? So yeah, I mean, the first point that we raised was, why is it warmer closer to the equator? That has everything to do with the angle of incident radiation from the sun. And the second thing is also related to the angle of incident radiation of the sun, because the Earth is tilted, we get a more overhead angle during the summer, a more lower on the horizon angle during the winter, and that explains why we don't get nearly as much energy per square foot, per square meter during the winter, which is why it's colder. Right? So, at this point, you might pause and say, well, can I explain to my next door neighbor why it is that it's colder during the winter than it is during the summer? And if so, that's good. Okay. Let's scroll further down. Okay. Now, this part is actually kind of related to what we're talking about here, because on here, you note that we get a lot more solar radiation closer to the equator, which basically means that we're going to be having a much warmer climate. If you actually look at the Earth on the equator, a great amount of the Earth is actually over the oceans, which basically means that the sun is striking most directly. It gets hot at the surface here, so we get a lot of evaporation. The air rises close to the equator, and basically as the air rises, it has to be replaced by air coming in from the latitudes that are further upwards, northern latitudes on the northern hemisphere, and southern latitudes on the in the southern hemisphere. And basically, if we get further up above, the air that's moving toward the equator has got to be replaced, and we'll see air sinking down, and this is going to be sinking roughly around 30 to 35 degree north and south latitude, right? So in other words, we get air that declines, air that is rising, air that is falling, and we get these circulations, right? We're not talking about circulations from east to west or north to south. We're thinking about within the Earth's atmosphere overall. If you think of all the air that's there around the Earth, the air is moving toward the equator, close to the surface, up near the equator, away from the equator, far away from the surface, and down right around the latitude where we live, right? 30 degrees north and south latitude, right? And so there's a name for these. We call these Hadley cells. Don't worry about that. But basically, the idea that the fact that the sunlight is striking most directly over the equator relative to elsewhere on the Earth's surface, it's actually resulting in this kind of circulation of air toward the equator, close to the Earth, away from the equator, further away from the Earth. And this sets up predictable patterns of wind, of air movement. Okay, and that's what we see later on in this chapter. So scroll up, and this is what I was talking about. Okay, air rises close to the tropics. This would be the equator right here. Equator. This would be the tropic of. I'll get back to my drawing. Okay, got to clear this out. This would be the equator. This would be the tropic. This would be where we are, the tropic of Cancer. This would be the tropic of Capricorn. Actually, I should be right here, 23.5 degrees. So I misdrew that. Cancer, Capricorn, and the area in between the tropics of Capricorn and Cancer are the tropical regions. But basically, the idea is that we've got circulation toward the equator, and as it moves towards the equator, it gets bent toward the west, right? As air is sinking this direction, the air gets bent toward the east, and the reasons for that are like really I'm having to restrain myself greatly to explain this to you. It's a process that you'll learn about if you take ecology. The Coriolis forces, it has everything to do with the geometry of the Earth. Okay, so if you're interested in that sort of, if you're interested in this sort of thing, again, remember this lecture is kind of a taster for a real class in ecology. Okay, and so in ecology, you'll learn why it is that we've got different kinds of habitats, different kinds um, of ecological communities in different latitudes along the Earth's surface, right? So there's that. And now if we move over to further down in the chapter, there's an explanation for why it is we've got these predictable winds. As I said, as the air is rising up from the equator, it's getting pushed toward the equator from the toward these northerly latitudes. But as the air is moving in this direction, it actually gets bent in a direction that's clockwise. In the northern hemisphere, it gets bent in a counterclockwise direction in the southern hemisphere, and that's due to these forces called the Coriolis forces. If you want to learn about it, take ecology. But this is why we get predictable winds that go from east to west in the area close to the tropics. It's the reason why we get predictable winds going from west to east in the area north 30 degrees north latitude, between 30 and 60 degrees north latitude, between 30 and 6 degrees south latitude. We get the westerly winds, which have been long known about by sailors. Sailors know that if they have to travel from the east to the west, they want to make sure that they get down into the tropical areas so they can take advantage of the trade winds and sail to the west. However, if you're moving from the west to the east, you want to do the opposite. You want to go further north, and so you can take advantage of the westerly winds, which are more predictably moving from in the direction that you want to go. Right now, what's neat about this is that right in between this area, in between the westerlies and the trade winds, you have an area where the air tends to be moving downward, and we generally get some high pressure and relatively few winds. The sailors call these the horse latitudes, and guess what? That's more or less directly where we live, right? And so these horse latitudes are associated with relatively mild climates and, more importantly, Mediterranean climates. Which, if you're living in Southern California like I am, like most MiraCosta students are, you're understanding that we've got warm summers, warm or dry summers, relatively little precipitation, but if you have any rain, it's going to happen during the winter, right? Which is a characteristic of the climate that occurs where you've got this relatively little activity when it comes to these general winds that are caused by the Hadley cells, right? And so, yeah, I mean, why is it so nice living in Southern California? I'm kind of bragging right now because it is late summer in the year 2022, and pretty much everywhere else in the United States, you've got ridiculous heat. Everywhere in Europe, you've got ridiculous heat. And so I'm looking at the weather forecasts for Southern California, and pretty much all summer long, it's been in the 60s at night and in the high 70s, low 80s during the day. And who's going to complain about that? Yeah, I know, I do. If it gets to like 83 Fahrenheit with 90% humidity, I'm saying, well, it's unbearably hot, right? And I talked to my friend in Texas, and my friend in Texas is saying, what are you complaining about? It's like, that would be like the most pleasant day here. Yeah, I mean, the question that I want you to think about here is, well, why is it so insanely nice living in Southern California? Well, it's partly because of our geographical location. We live right off of an area of the ocean where we don't have a whole lot of air movement, which means that we're able to generate these high pressure zones, which is going to keep the weather nice and sunny during the summertime, which is going to keep us being pretty well. And at the same time, we have the marine influence, the onshore flow of air from the coast is going to keep a pretty steady flow of relatively dry air over our heads. Okay, can't complain about that. Okay? But this also means, I mean, what this is great about it, great thing about this is that you can predict that if you go to a similar latitude in the southern hemisphere, like off the coast of Chile, off the western side of the continent, you would expect the same type of climatic condition in which you would get a Mediterranean climate. And you do, right? If you go to Viña del Mar, which is a beautiful city on the coast of Chile, they've got more or less exactly the same kind of climate that we have here in Southern California, right? If you go to the coast of Africa or the coast of Africa in the south, like around South Africa, right? Or if you go to the west coast of Australia, these are the places where you got Mediterranean climate. And it's all because of where we are on the continent relative to a large ocean mass, right? Right? And yeah, I think to me at least, it's pretty exciting to understand these things. Maybe more so for me, because living in Southern California, I'd like to understand why it is that we have the kinds of climatic conditions that would make me really have to think twice about ever moving away from this area. Right? I know I'm bragging. And I just think that's the truth, right? Now, another point, this is a follow-up to what we just said, right? We know that the Mediterranean climate is in the Mediterranean, which basically means Spain. So let me get my drawing thing. Okay, Spain, Northern Africa, Italy, this whole area here, right? That would be the Mediterranean. If you look at the position of Mediterranean climate in North America, it's actually a little bit further south compared to where you are in the actual Mediterranean, right? The Mediterranean, you know, this is a crazy factoid, but this is the island of Sicily, right? Which is kind of like at the bottom end of the Mediterranean climate. If you actually move directly to the same position in North America, you get to New York City. And New York City is like it's a cold place. I mean, it's actually further up than that. It's pretty damn cold, and you wouldn't. It's surprising to think that New York City is at about the same latitude as Sicily, which is like the southern, which is the island off of the tip of the boot of Italy, right? Well, no, that's not altogether that mysterious, because in addition to everything else we've been talking about, you've got other influences like the oceanic currents. The Gulf Stream basically carries a big pulse of warm water towards the north of Europe, which explains why it is that England and Ireland can be so far north and not have the same kind of ridiculous cold that you have in Newfoundland and the same latitude in North America, right? Most of Europe takes benefit from the Gulf Stream carrying warm water from the equator up to the northern portion. And this is what we were talking about in the previous video, the idea that the evolution of the Earth, the geological evolution, the way that the continents are sitting, this Africa there, South America there, North America here, is going to create a pattern of circulation in the oceans that's going to result in warm water from the equator basically being pushed up toward Northern Europe, which is going to keep Europe generally being a lot warmer than you would expect, given its northerly latitude. Okay. Intrigued? Yeah, this is a shameless plug for our ecology classes, because if you haven't thought about this kind of thing before, and it's pretty intriguing and pretty fascinating. Okay, no, one more thing. Okay, just one. I promise. This is it. Right. Here are these drawings. And this is directly related to life in Southern California, right? And it has to deal with the fact that we know that we've got a world in which if you go far enough east, and let's maybe we're Southern Californians here. Let's think Julian. You know where you go for the apple pies? Okay. Yeah, that's up in the mountains. If you go past Julian, you're directly in Anza-Borrego, right? You can actually observe the rain shadow. This is called the rain shadow effect. The air laden with water is coming off of the Pacific Ocean. It rises up. As it rises up, it gets a little bit cooler. Rain falls. Okay. Then you have a little valley, and it rises up again, maybe more severely. As it rises up, the air cools, and that causes it to reach the dew point, and the rain falls. And so by the time that same air mass reaches the desert east of Julian, there's no more water in that air mass. And so you get this dry air passing over the overhead east of Julian. And so, yeah, I mean, if you have the coastal range, you get, it's still relatively dry. I mean, there's relatively little moisture coming in off the Pacific Ocean. We do, after all, live in a Mediterranean climate. Less moisture by the time we get to the mountains over Julian, but that's a more severe climb, as you'd still get a wet area on the western slope of the mountains near the apple pie region. And then as that air goes over to the east, it falls, it cools, it dries, and you get Anza-Borrego, where it's pure desert. And so, I mean, this is another thing that we're looking at. You can experience this directly simply by taking a drive from Oceanside on the 78. You get to the Wild Animal Park, the San Diego Zoo Safari Park. You're still in this area. You drive up the hill through Ramona, get up to Julian, and then you come back down to the other side. You're in the desert. Within the span of 2 hours, you can go from the ocean to the desert and see everything that we've just described. It's all related to the Earth's topology, the surface of the Earth, the contours of the Earth, and the fact that the air is moving in from the ocean, rich with some amount of water, right? The evaporation of the ocean surface is what gives us the water-laden air that's moving off the coast. And we get some moisture in the coast range, more moisture in the interior range. By the time it gets past that interior range, there's practically no more moisture at all to fall in the desert. Okay, let me go to my whiteboard share. Okay, so answer these questions for me. Okay, why is it warmer in Costa Rica, which is 10 degrees north latitude, relative to Oceanside, which is roughly 37 degrees north latitude? Why is it warmer near the equator? Yeah, remember that? Rewind the video if you need to, right? Why is it warmer in the summer and colder in the winter? Winter is when the sun is, right, at a lower angle compared to the summer. And being at a lower angle, you're going to have less energy per square meter because, light passing down from directly overhead is going to be intercepted over a smaller area compared to light coming in from a lower angle. Right? How is this related to the fact that we've got ridiculously pleasant conditions climate-wise in Southern California relative to the rest of the world? Yeah, I know. You could be a weirdo that says, oh, no, I like it when it's super hot and humid, or I like it when it gets so cold because of the seasons. Yeah, right? I like to have seasons. No, okay, legitimately, fall in Chicago was not terribly bad, but pretty much every other season besides the fall, I would much rather be in Southern California, right? Why is it so nice in Southern California? Well, it has everything to do with the position that we are on the continent relative to the equator and relative to the Pacific Ocean. Okay. Even though New York City and Sicily are at the same latitude, why is it so much colder in New York? Or actually more, it's more appropriate to say, why is it atypically warm in Sicily and in Europe generally compared to where you don't have the Gulf Stream? Oops, just gave you the answer. Okay. And the last question is, well, why is it that when you get to the other side, the backside of the hills, Julian, you drive down into what amounts to a very, very dry desert? What's the story there? Yeah, I think you could answer these at this point, right? And so this little break from clinically focused biology has been entirely worthwhile, wouldn't you say? Okay, see you really soon.